Okay, so welcome you all again in the session 2 of day 1. We have again the expert Venkateswar Rao. So I invite Venkatesh sir to continue the session. Thank you.
Yes, thank you. Am I
Yes,
audible?
sir.
Screen is visible now.
Yes.
So you have stopped here, right? So
Yeah.
we had discussed different, basics of machine learning, things like gradient descent, regularization, linear regression, logistic regression, all these basic concepts that forms the basis for neural networks we have discussed. So let's have a look at this actual neural networks now, neuron or a perceptron. This is artificial neuron. Again, is the single biological neuron, that whatever we have seen in the previous slides. So artificial neural networks with a single neuron cell is equivalent to logistic regression. So with a single artificial neuron, it is equivalent to the logistic regression. So first we will understand this logistic regression with a neural network mindset. Then we would explore the ANN with multi-layers and neurons. So logistic regression, if you see what we are doing, we are trying to compute the net sum first, isn't it? That is theta naught, x naught, theta 2, x2, theta 3, x3, so on, theta n, xn, isn't it? So the net sum we are trying to compute, then we are passing it to the sigmoid function. Correct. So first we are computing the net sum, then we are passing it to the sigmoid function. Similar to your biological neuron, it gets the all the spike signals from the dendroids and then integrates them. If after integration, if it is greater than certain threshold, then neuron fires. Otherwise, it's not, right. Here also, if it is greater than, then threshold, then it is +1. Otherwise, it is -1, something like that, isn't it? So we'll try to understand this logistic regression with the neural network mindset. So these are the inputs that we are passing to the neuron, isn't it? Similar to the inputs that we have in logistic regression. And these are the edge weights, similar to the parameters theta naught to theta n that we have in the previous case, logistic regression. Here we are computing the sum, then we are passing it to the sigmoid function. The same thing we are doing in case of logistic regression also. So we can say that artificial neural network with a single cell is equivalent to logistic regression. What is neural network then? We have seen a single neuron, isn't it? Single artificial neuron. What is neural network? A group of these artificial neuron units together form a neural network. So this is the simple neural network example in this figure. So this input is a layer x1, x2, x3. This x0 is equivalent to 1 anyway, and to add that bias term to have a common representation, we have added x0 here, which is a bias. And in some cases, you have a separate x0 for each and every, yeah, of course, this, yeah, once you have this x0 as a 1, you have a separate bias for each and every activation unit, right? Yes. So this also a bias term. To have the bias term, a0 we have added in this case. These are the actual inputs, x1, x2, x3. And we compute this net sum and then pass it to the activation function, that is the sigmoid. We get this, and here also with the different weights we does the same, with the different weights we does the same here. And then these, taking these activation units, output of these activation units as an input to the next layer, and so on. Okay, so this is a simple 3-layer network in which layer 1 is the input layer, layer 3 is the output layer, and layer 2 is a hidden layer. Okay, so just remember, hidden layer, neural network with one hidden layer, we call it as a shallow neural network. Neural network with more than one hidden layer, we call it as a deep neural network. The deep neural network has got more hidden layers in contrast to the shallow neural network, wherein we have only one hidden layer. Okay, so that is the difference between the shallow neural networks and the deep neural networks. Of course, in deep neural networks, there are other variations also, but the basic thing is that In deep neural networks, we have got more layers, more hidden layers, in contrast to single hidden layer in case of shallow neural networks. Got it? So why do we need this neural networks? We have so many methods, right? Like we have linear regression, we have logistic regression, all these different methods are there, right? Why we should come for this? What is the need of this neural network? So let's look at how linear and logistic regression learns complex nonlinear hypotheses. Linear regression or logistic regression are there for linear data, right? So if your data is linear, if you want to learn the linear hypothesis, then those are absolutely fine. But the data may not be linear always; it may be in the form of nonlinear. So if you want to learn the nonlinear hypothesis, how do you learn using this linear regression or logistic regression? Let's have a look at the linear regression. For the same example, house price prediction example. So if you have a linear regression model, this is how it looks like, right? In case of linear regression, you are trying to fit a line to the data. So this is how it looks like. But the data is not looking like linear, right? It is some form of non-linear, isn't it? So if you apply linear regression, it is like theta naught plus theta 1x, which forms a line. If you apply second order polynomial, this is a better representation than your linear hypothesis, isn't it? The second one, it's a better representation for the data, correct? So second order polynomial is what? Theta naught plus theta 1x plus theta 2 x square, isn't it? The same x, you are taking the second order polynomial, theta 2 x square. Similarly, if you go for the third order polynomial, it is theta naught plus theta 1x plus theta 2 x square plus theta 3 x cube. This is with a one variable. If your input has only one variable, that is size in square feet. If your input has got multiple variables like a number of bedrooms, number of bathrooms, number of floors, number of what is that, age of the house, all these different variables. If you have multiple variables, how do you go for the polynomial regression? Suppose if you have two features, x1 and x2. And if you want to order the first order polynomial, your hypothesis looks something like this, right? Theta naught plus theta 1 x1 plus theta 2 theta wait okay theta 2 x2, isn't it? This is how it looks like, right? For first order polynomial. If you go for the second order polynomial, you have to consider all the second order combinations like x1 square, x2 square, x1, x2, all these varieties of second order polynomials you have to consider. Similarly, if you consider third order, you have to also include third order terms like x1 cube, x2 cube, x1 square, x2, x1, x2 square. All these varieties of combinations with the third order also we need to include. This is the similar with the logistic regression also. Only thing is h theta of x is a function of all this. After you find out this quantity, you have to give it to the sigmoid. That is the only difference between the linear regression and logistic regression. So if you want to learn the nonlinear model, you will have lot of parameters. That is what I am trying to say. So if you have a third order polynomial, you see you have 10 parameters, theta naught to theta 9, isn't it? With two variables, with two input features. Imagine you have 100 features and you want to learn the second order polynomial. How many features would you have? It would be around 17,000 features and 17,000 parameters you will have to learn. Okay, do you think it is a wise decision to learn those many parameters? Isn't it? It is very time intensive, right? If you want to learn 17,000 features, isn't it? And still you're not sure whether you'll be able to learn the hypothesis accurately or not after that much of process also, isn't it? So let's look at a problem first, then we'll also see how the neural network problem solves this, neural network solution solves this problem. Okay, so let's have a look at this nonlinear classification example. Example that I took is XOR or XNOR. You know this gates, right? Given two inputs, it will produce some output, isn't it? What is XOR gate output? Given 0, 0, 0, 1, 1, 0, 1, 1. If both the inputs are same, then it is 0. If they are different, then it is 1. isn't it? That is what XOR performs. XNOR is opposite of this. If both the inputs are same, then it is 1. If they are different, then it is 0, isn't it? So you can represent it that way, right? XNOR as shown in the figure, isn't it? If it is 0, 1, then it is 1. If it is 1, 0, then also it is 1. Oh, sorry, this is XOR. I think it's 1, 1. It is 1, 1. It is 1, 1. It is no, 0, 0, 0, 1, 1. It is 0. Oh, no. Yeah, anyway. Yeah. So if it is different, then it is one class. If it is same, then it is another class. It represents the both, in fact, isn't it? So crosses here represents one class, and circles here represents another class. Okay. And this is the data generated for using this gates XOR or XNOR, isn't it? Is this a linear class? Linear data, linear classification example? No, right? We cannot draw any line to separate these two classes, isn't it? We cannot draw a single line to separate these two classes. So it's not linear. We should have some nonlinear hypothesis to classify the one class from the another class, isn't it? So if it is not linear, your logistic regression will not work here. Suppose if you just draw a one line here, it will not be able to separate both the classes. Therefore, logistic regression fails here, isn't it? Again, suppose if you extend this to polynomial order some function to the nonlinear hypothesis, I mean to the another dimension, if you bring them up, then there is a problem of so many parameters. Okay, so how neural networks solve this problem we'll see, but then we'll try to build up simple gates with using this logistic regression or a single perceptron. Okay, so simple example that we have taken is AND gate. What is AND gate says? If both are 1, then both the inputs are 1, then output should be 1. If both the, if at least one of the input is 0, then it is 0. Okay, so let's see whether that is achieved or not using these weights, minus 30, 20, 20. So the weights that we have taken in this network are minus 30, 20, 20. Okay, so x not equal to 1, that's what we said, right? So here we have to compute the net sum first, that is minus 30, which is the bias unit, plus 20 times x1 plus 20 times x2. 20, 20 are the weights associated with that links, isn't it? And this we pass it to z, which is the sigmoid function, 1 by 1 plus e power minus z. Okay, so if, say suppose x1 is 0 and x2 is 0, what is this net quantity? That is equivalent to minus 30. Isn't it? So what is z of minus 30? 1 by 1 plus e power minus of minus 30. Okay, which is a very big quantity at the denominator, isn't it? 1 by very big quantity is almost equivalent to 0, isn't it? So we got 0 at the first entry. Say for example, you have inputs as x1 equal to 0 and x2 equal to 1. And if you substitute in this equation, it would be minus 10, isn't it? Minus 30 plus 20 plus 0. Sorry, plus 0 plus 20. Okay, which is equivalent to minus 10. And z of minus 10 is also very big number in the denominator, 1 by very big number, which is almost equivalent to 0. Similarly is the case with 1, 0 also. And with 1, 1, this quantity would be 10 because minus 30 plus 20 plus 20, which is equivalent to 10. Z of 10, 1 by 1 plus e power minus 10. E power minus 10 is a very negligible quantity, which is almost close to 0. So 1 by 1 plus 0, this is equivalent to 1. So our AND gate is fulfilled, correct? With these weights, minus 30, 20 and 20. Correct. Let's also learn the OR gate with another perceptron with a different weight. Weights here are minus 10, 20, 20. Okay. So these are the weights. With these weights, I get an equation of h theta of x equal to z of minus 10 plus 20 x1 plus 20 x2. Isn't it? So similarly, if I compute by substituting x1 and x2, I get these weights. So 0, 1, 1, 1. If both the things are 0, then only it is 0. Otherwise, it is 1. That is what OR gate performs, right? So with this one single perceptron, I can design OR gate. Similarly, with one perceptron, I can design AND gate. I can also design NOT gate by just taking 10 and minus 20 as the input. If it is 0, I am getting 1. If it is 1, I am getting 0. Okay, so using this NOT gate, I mean, I can also design not x1 and not x2 gate, isn't it? Not x1 and not x2 gate weights are 10 minus 20 minus 20. What is not x1 and not x2? If both the things are 0, then it is 1. Otherwise, it is 0. That is what not x1, not x2 says, isn't it? Just give me 1 second. Okay. Sorry for this. Am I audible?
Yes.
Yeah, okay. So I can also design this not x1 and not x2 using the single perceptron. That is, when both the things are 0, it is 1, otherwise it is 0. Isn't it? Now the question is, these are multiple linear models, isn't it? Whether I design for AND gate or whether I design for OR gate, whether I design for not or not x1 and not x2, all these we have designed using the linear models. That is logistic regression or perceptron, isn't it? Now the question is, can I combine multiple linear models to get a nonlinear model? Okay, so how do I do that? This is how I can do it, right? Now so if I see these are the inputs x0, x1 and x2, and if you see this gate, this is this gate, isn't it? Minus 30, 20, 20. Sorry. Minus 30, 20 and 20. Minus 30, 20 and 20. So this is the AND gate, isn't it? Similarly, this is a not x1 and not x2 gate with weights 10 minus 20 minus 20, isn't it? 10 minus 20 minus 20, isn't it? So 10 minus 20 minus 20. So this is not x1 and not x2 gate. So now if you observe the corresponding outputs, when I give 0, 0, 0, 1, 1, 0, 1, 1, this is the AND gate output. That is, when both the things are 1, then only it is 1. Madam, some doubt? Okay. So, and similarly, this one is a not x1 and not x2 gate. That is, when both the things are 0, then only it is 1, otherwise it is 0. Okay. Now I pass these two as input to the next layer, isn't it? With including bias term here. So this is a OR gate. So from these two inputs, that means when at least one of them is 1, then is 1, otherwise it is 0. Okay. So I can get this 1, 0, 0, 0, 1. Okay, isn't it? This is the outcome is just x1, x0, x2, isn't it? Isn't it amazing? So you combine multiple linear units to learn the nonlinear hypothesis. That is x1 times, x1, x0, x2. That you couldn't learn using the single perceptron or a linear regression, logistic regression model, isn't it? So our neural network is able to learn complex nonlinear hypothesis. So this gives the motivation for why we have to go for neural networks. Understood? Following me? So we'll go. Now we'll try to understand this in depth. This is the motivation for why you have to go for neural networks. Now we'll see the notations and in details of the neural networks. So this is a network which has 3 layers: input layer, hidden layer, layer 2, output layer. Okay. Here x0 and a02, that is, these are the bias terms. If I'm superscripting with something, it means that it belongs to that layer. So here I'm superscripting with 2, right? It means that all these units have belong to layer 2. And the subscript indicates the unit number in that layer. This is the 0th unit, first unit, second unit, third. Total 4 units are there. Okay. So layer 1 and layer 2 have 3 units each and 1 bias term each. And layer 3 has 1 unit. Aij is the activation of unit I in layer J. Okay, that's what I said, right? AH. Zij is the net sum at unit I in layer J. That is Aij equal to Z of Zij. Okay, that sum we are computing, no? Theta transpose X or W transpose X. That is this Z. Okay. And theta J is the matrix of weights controlling function mapping from layer J to layer J plus 1. Means all the weights here are theta 1, all the weights here are theta 2, and so on. Okay, how many weights will I have here? Suppose if I have 3 units in layer 2 and 3 units at layer 1. Okay, so what is the dimensionality of the weight matrix here? Which is 3 by 4, isn't it? 3 times 3 plus 1 by adding bias term, isn't it? So this is forward propagation. We start with layer 1, in which we have input layers. We compute each and every term in this second layer. Then we pass this as an input to the next layer. If we do till the last layer, that is forward propagation. So what is happening here? A12, which is equivalent to theta 101, the corresponding weights here. Okay, 10 represents the weight between unit 1 in layer 2, layer 1, and unit 0 in layer 0. Okay, I mean that is how it is represented. Or okay, this is theta 1. So this is the weight between this theta 10 is weight between these two, A1 and X0. 1 represents, this is after the first layer. Okay, and similarly if I have some weight between 1 1, it means that this is the weight between A1 and X1. 1 2, this is the weight between A1 and X2. 1 3, which is the weight between A1 and X3, like that. Okay, so I use these weights and inputs, multiply them and add them together, which is the net sum that I'm getting, theta transpose X, and I'm passing it to the sigmoid function. I get this activation unit, this one. Similarly, I compute activation units A2 to A3 to. Once I have this, I can compute H theta of X, which is my prediction, isn't it, for the next layer. If I have another layer, I will have another again activation units and so on. Okay, so I use again these activation units as an input. I compute that. I first calculate net sum theta transpose A. A is that A02, A12, A22, A33, and so on. This process is repeated. Okay, so this we call as forward propagation. We are starting from the input layer, moving towards the inner layers, layer by layer. We are computing the activation units, and these activation units act as input to the next layer, and so forth. Okay, finally we get output unit, that is H theta of X. All right. So now question for you. Oh, I think this is answered. From the equation above, one can generalize if the network has Sj units in layer J and Sj plus 2 units in layer J plus 1, then theta j is the dimension of Sj plus 1 times Sj plus 1. Okay. So this I have already told you, right? If we have 3 units in layer 2 and 3 units in layer 1, then this theta 1 will be of dimension 3 by 4. Okay, isn't it? The same thing, it is generalized here. This is forward propagation. Okay, so if you want to do vectorization of this, it is, you can take we can compute A1 as Z of theta transpose X with these theta values, and you can also compute theta 2 as G of that, and so on. Okay, just compute that. Similarly, here you can see the vectorization, right? G is Z1 of 2, where Z1 of 2 is equal to theta 1 transpose X. Okay. All right. So you can have a look at this, right? So this Zj is equivalent to theta j minus 1 times A j minus 2. This is the vectors. This is how you are computing net sum. And once you get the net sum, you can directly pass it to the sigmoid and get this. Okay. So this is like a vectorization of the same thing that we have discussed in the previous slide. Vectorization is important because to take the computational advantage of the computer architecture. So this is for the single class we have discussed, right? If it is 1 or 0, h theta of x is close to 1, that is 1, h theta of x is close to 0, then it is 0, isn't it? That is for a single class. I mean, two class problem, binary classification problem. What if you have multiple classes? Like for example, if you want to determine whether image given to is a pedestrian, car, motorcycle, or truck. There are four classes, right? You have to classify the image as one of these four classes. Okay, so in those cases, you will have four output layer, four units in the output layer. Okay, and the vector 1000 represents the pedestrian, the vector 0100 represents the car, and the vector 0010 represents the motorcycle, and the vector 0001 represents the truck. Okay, so that is how you model multi-class classification problem. So in case of multi-class classification problem, in the output layer you will have multiple output neurons. Okay, as many number of classes as you have in the data set. So the cost function of the logistic regression is this, right? 1 by m sum over I equal to 1 to m yi log xi plus 1 minus yi log 1 minus hi plus regular regression. This we have already seen. Yes.
Vector sir, sorry to disturb you. All the participants are informed. Please mute yourself because the background noise is coming. It is requested to please mute yourself all.
Some noise is coming here also.
Yes. Okay, sir. Okay.
I think my neighbors are fighting.
Oh, okay.
Okay, anyway, ignore that if you get some noise.
Okay.
So this is the cost function of the logistic regression, isn't it? So that's what we have seen. We have seen the intuition also behind this, wherein we have two classes only. That is why we can model it with one output neuron. But in case of multiple classes, you cannot model it using a single output neuron. So that is why you have as many number of classes, output neurons as many number of classes as you have, isn't it? So cost function of neural network with L number of layers and K number of classes and SL number of units in layer L. I mean that number of units in layer L is indicated with SL. Okay, isn't it? So with that, the cost function can be defined as it is just sum over all the units, isn't it? So you're just taking extra sum over here, that is k equal to 1 to k, which is k is the number of classes. What is that you're doing is that for each and every output neuron, you are computing the cost and taking sum over all these classes, all these output neurons. That is what you're doing. It is just the same. You just see that, you just observe, it is just the same. But the thing is that you're taking this with respect to each and every output neuron and taking sum over that. And this regularization term, it is earlier you have considered n thetas because earlier you have n parameters. Now you have so many parameters, right? Between the layers you have so many parameters. So all those parameters you are considering here in the regularization term. That is for L equal to 1 to L minus 1 for all the layers, and between the layers you are taking each and every weight, okay, or parameter. So you're just considering all the parameters in the network. Here you're just considering all the parameters in the model. So that is very simple difference, isn't it? You're just extending this cost function of a single neuron to the cost function of a network, isn't it? So that's all you are doing in this cost function. You just extended that. So how do you learn these weights? How do you learn these parameters? Earlier, because we have n parameters, you just used gradient descent to compute that. So you have a cost function, you have a parameter to learn. So with respect to each and every parameter, you took the derivative of the cost function and updated each and every parameter, isn't it? That's what you have done, correct? So you have a cost function. With respect to each and every parameter, you took the derivative and you updated that parameter, isn't it? Theta j equal to theta j minus alpha times derivative of j with respect to j. That's what the gradient descent algorithm that we have applied on the applied on this logistic regression or linear regression. So how do you learn weights here? In this case, here also the same thing you can do. That is simple brute force way of extending that logistic regression gradient descent to the neural network gradient descent is that you compute gradient descent with respect to each and every weight in the network. Okay, you have multiple weights, right? All these weights are the parameters of your model, neural network. Okay, so you compute gradient descent with respect to each and every parameter. Okay, I think noise is too much. Is it? Is the noise too much? I'll close all the doors.
Yeah, if it is, if you can close, it is good.
Yeah, wait, give me 1 minute. Huh?
Sure,
Sorry.
sure, sure.
Is it better now?
Yes, yes.
Okay. Okay, so simple way to extend that gradient descent algorithm for a simple perceptron to the neural network is that here also we can compute gradient with respect to each and every weight or each and every parameter in the network. And then we can apply gradient descent to update the weights, that is theta j equivalent to theta j minus alpha times derivative of j with respect to that particular parameter theta j. Okay, but then it is very time intensive and redundant calculations. You may be calculating the same thing again and again. Okay, so that is why we have a solution called a backpropagation algorithm. So in backpropagation algorithm, we avoid redundant computations. We don't compute the same quantity again and again. Once we compute, we store it in a table. It's a kind of dynamic programming. So the same thing you are doing in dynamic programming also, right? So you are computing something, you're storing it in a table, and you're using it again. Okay, and then after that you again store it in the table, and again you use this quantity, isn't it? So that's the same thing iteratively you are doing, isn't it? Step by step. In case of backpropagation, in case of dynamic programming, the same thing we do, similar thing we do in case of backpropagation algorithm also. So this backpropagation algorithm avoids redundant computation. How? We'll see that. So we'll just look at the forward propagation first. So activation unit at layer 1, I can just take it as the input. A1 is input. Whatever the input that I got, x1, x2, x3, so on, x0, x1, x2, x3, so on. And Z2, that is net sum at layer 2, is theta transpose A, isn't it? A1, theta 1 transpose A1. That is, I'm just multiplying these and taking sum over that. Okay, which is the vectorized implementation. And once I get sum over that, I can pass it to the sigmoid function and can get activation units at layer 2 by adding bias term A0 2, isn't it? So I repeat this procedure till the last layer, that is AL minus 1, Z of ZL minus 1. And Z capital L is the last layer, that is the output layer. So net sum at last layer is Z capital L, which is theta L minus 1 times AL minus 1. And then I can compute the prediction, or I can also refer to it as A capital L, because it is activation unit at the last layer. We have capital L number of layers in total, okay, which is equivalent to Z of Z capital L. This is forward propagation. We are starting from the input layer. Layer by layer, we are computing this net sum and the activation units, and these activation units are again passed as the input to the next layer, and so forth till the last layer we are computing this, finally getting the prediction H theta of X. This is forward propagation, isn't it? So once I have completed this forward propagation, I should be able to update these parameters based on the cost that I got at the end, isn't it? Tell me one thing. Say for example, Krishna sir and Vikas and somebody else is organizing this workshop. If something goes wrong here, okay, say for example, this Vikas might have spent some 20%, 30% effort. Krishna sir might have spent some 30% effort. Other guy might have spent another 30, 40% effort. If something goes wrong here, how much blame that Vikas will take, or how much blame Krishna sir will take, or how much blame somebody else will take? The say in the similar proportions, right? If Krishna sir spends 50% effort to organize this, if something goes wrong, he should take 50% blame, isn't it? So the error that has got at the output should be propagated back to these individual neurons that are responsible for that output, isn't it? So that is what the back propagation does. It propagates the error towards the backward. Oh, sorry. Okay, so the h theta of x or AL is the prediction at the last layer, isn't it? So in order to reduce the error between the prediction and the actual value, back propagation is used. That is known fact. What at the end, what you want? We want to reduce the error between the prediction and the actual value, isn't it? Whatever the model that we use, either it is linear regression, logistic regression, neural network, this thing, that thing, SVM, decision tree. At the end, what we want to minimize the error between the prediction and the actual value. Okay. So say, for example, delta Lj is the error of node j in layer L. Okay, it means that this is the error associated with the prediction made at that particular node, ALJ. Okay, so back propagation aim to calculate this error term, propagating backward starting from the output unit in the last layer. So you start with the last layer error, you propagate this error towards the backward. So for each output unit in layer L, the term is given by this error term is AL minus Yj, ALJ minus Yj. That is, ALJ is the predicted value, Yj is the actual value. You compute the difference between these two, that is the error at the last layer. Okay. Achha, this is with respect to the sigmoid activation function only. If you take a different function, it will vary slightly, but I just wanted to demonstrate using the concept using the, I'm getting some noise. I don't think it is at my end. Okay, thanks. So this is the error at the last layer, delta L equal to AL minus Y in a vectorized implementation. So for all the output layers, you are computing the difference between the actual and the predicted. Predicted is AL and the actual is Y. Okay, so this is the difference that you are calculating at the last layer, which is the error at the last layer. All right. So once you get error at the last layer, you can compute the error terms for the previous layer using this equation, delta L equal to theta L transpose delta L plus 1 times derivative of J with respect to ZL at that particular node, which is equivalent to AL times 1 minus AL. Just hold with me for 2 minutes. You may be finding it little confusing, but your all doubts will be clear. Don't worry about it at all. Okay. So you can see this, you're multiplying this error with the corresponding weights, isn't it? Like I have told you, if somebody is 50% responsible for this error, you're propagating 50% error back, isn't it? So this delta term is taken care there. And this is the additional term Z dash ZL. What is the error at that particular node? Okay, error propagating it back from the previous layers plus error at that node. Okay, times error at that node. So which is equivalent to derivative of Z dash Z is derivative of sigmoid function with respect to ZL. Z of Z is sigmoid function, right? Z dash ZL is derivative of sigmoid function with respect to ZL. That is equivalent to AL times 1 minus AL. Okay, and this you will repeatedly do the same. you will back propagate and compute error at each and every layer till layer 2. Why you have to stop at layer 2? Why not at layer 1? Because layer 1 is input layer. You are not assuming that any error associated with that layer. Correct. So now the gradient for the cost function, which is needed for the minimization of the cost function, is given by this. You can directly compute this derivative of j with respect to theta Lij using this Alj times delta IL plus 1. What you are doing, you are computing error terms at each and every layer, and you are using activation units and this error together to compute derivative of a cost function with respect to a particular parameter. Isn't it? You are not every time calculating the gradient. You just observe that. I want you to observe that every time you are not computing the gradient with respect to a particular parameter. You are doing some general procedure, and using that procedure you are computing, you are directly arriving at this derivative of j with respect to a particular parameter. Okay, with the example you will see that will be very clear, but I want you to hold with me for 1-2 minutes. Understood? So on the whole, this is what you are doing, isn't it? So you're initializing all the delta Lij to 0 for all ijl for all the parameters. This it shouldn't be 0 actually always. It should be a random value. There is some mistake in this. If you initialize zeros, your network will learn very slowly. So it should be some random value. Delta Lij, all the parameters initially you are initializing it to some random value. Here in this case, it is shown as 0. And for I equal to 1 to m, this is for all the examples you are doing the same, not just for the one example. So all the examples in the training set, you are doing this. You are setting A1 to be xi. That means that input layer you are setting as the input. Input A1 is the input layer, correct? So A1 equal to xi you are setting. It means that you are just passing input as the layer 1. Layer 1 as the input, sorry. So perform forward propagation to compute AL for L equal to 1 to L. So using forward propagation, you compute A2, A3, A4, and so on till the last layer, isn't it? We know how to compute. And after you go to the last layer, we compute the error at the last layer, delta L, delta capital L. Okay. So after computing this delta capital L, we compute this error at the previous layers using the backward propagation. Okay, so we compute error at the previous levels, that is the delta L minus 1, delta L minus 2, so on, delta 2, using the back propagation algorithm. You know how to compute. We have already seen the equations to compute. Okay, so once you get that, you can compute the derivative part by just summing up this Alj times delta Lij over all the examples and then take the average over that. You can see this is what derivative with respect to a particular example, particular parameter, correct? So this you are computing for all the examples. I'm sorry, though this is delta Lij is equal to 0 only. I'm very much sorry. I thought it is theta Lij. Sorry. So this is summed over all the examples, isn't it? It is the vectorized implementation of the same. And then finally you are getting this derivative that is equivalent to 1 by, you are just taking average over that. And this is the regularization term. And if j equal to 0, it means that you will have no regularization term here. You just take some average over that. And this is your final derivative of j with respect to theta Lij. This dLij is equivalent to derivative of j with respect to theta ijl. Okay, little complex, but we'll try to understand with the example. I'll just repeat this because it may be a little confusing. So you are initially taking input. Your layer 1 activation units are your actual output. So you are setting A1 to xi. Okay, and then you are performing forward propagation to compute activation units at the next layers, A2, A3, A4, and so on till the last layer. Once you get activation unit at the last layer, which is your prediction, A capital L, you are determining the error at the last layer, that is delta capital L, which is the difference between AL minus YA. Now, this error is propagated backward using this backward propagation algorithm. That means you are computing errors at the previous layers by using the backward propagation algorithm. That is delta L minus 1, delta L minus 2, so on till delta 2 you are computing. Once you get this, you have to determine what is derivative of j with respect to a particular parameter. That you are doing using this equation. You're taking sum over all these things that you have computed, I mean average over all these things that you have computed, plus this is the regularization terms derivative. Okay, because in the regularization term you don't have theta 0. Okay, so that is why you have here no regularization term. Okay, so this is your derivative of j with respect to theta ij l. Okay, all right, now we have lot of procedure that is well defined, and finally we are saying this quantity is equivalent to derivative of j with respect to theta ij. I mean, we are actually saying, what we are actually trying to say is that you need not compute separately theta j with respect, I mean derivative of j with respect to, sorry, derivative of j with respect to each and every parameter. You need not actually you need not repeat this procedure every time. There is some procedure, so if you follow that procedure, you can actually compute the same thing using that procedure. That's what we are trying to say. Now we'll verify whether that is same or not. Whatever we are getting through this back propagation algorithm, and whatever that we actually compute the gradient descent and derivative directly, whether both are same or not. We'll verify that. Okay. So for that demonstration, I just took a simple example with with 3 layers again. Input layer with 2 units, hidden layer with 2 units, output unit with 1 unit. I avoided bias term for the simplicity. Okay. So initially we are setting A11 to X1, A12 to X2. That is layer 1 is the input layer. Okay, isn't it? So I can compute net sum here by using these terms theta 111 X1 plus theta 112 X2. And I pass this to sigmoid function, I get this activation unit. Similarly, I take these two inputs with the different weights, I take net sum and pass it to the sigmoid function, and I got this activation unit A22, isn't it? Now I have different terms, different weights with these inputs A12, A22, and I can compute A13, isn't it? I can compute net sum using these two, and again I pass it to the sigmoid function, I get A13, which is equivalent to h theta of x. So A13 is my prediction. Correct. So this is forward propagation. That is how I do forward propagation, isn't it? According to the procedure that we have defined. Now, suppose I want to update this parameter theta 112. What I actually do, I have to take derivative of j, that is my cost function, which in this case, because it is a binary classification problem only, it is same as the logistic regression cost function. We just add minus here. I forgot everywhere. Okay, so which is my cost function. So I have to take derivative of j with respect to theta ij, and which means in this case it is here theta 112, and I update theta 112 equal to theta 112 minus alpha times derivative of j with respect to theta 112. Simple, very simple, right? So how do I do that? How can I compute this derivative of j with respect to theta 112? I can write this as these three terms using chain rule, isn't it? I can write this as derivative of j with respect to h theta of x times derivative of h theta of x with respect to z13 times derivative of z13 with respect to theta 112. Using the chain rule, I can write this the same thing, isn't it? So let us individually compute these terms. This is the derivative of j with respect to h theta of x, which means the derivative of j means this one with respect to h theta of x. So if I do that, yi times derivative of log h theta of xi with respect to h theta of xi is 1 by h theta of xi. Similarly, plus 1 minus yi times derivative of this log 1 minus h theta of xi is this 1 minus h theta of xi times minus 1, because I have to take derivative of this term also again, which is equivalent to minus 1. isn't it? So this I can write it as yi minus h theta of xi divided by h theta of xi times 1 minus h theta of xi, isn't it? So the same thing I can write it as this. So I've got derivative for the one term. This is the first term. Okay, what is the next? So this, let's take this derivative of z13 with respect to theta 112. What is z13? Which is the net sum net layer 3, which is equivalent to this. That is theta 112 times a12 plus theta 122 times a22. Okay, I mean pay a little more attention because the notations may confuse you. Just taking this net sum here, that is z13. So if I take derivative with respect to theta 112, which is this term I'm trying to compute, which is equivalent to a12, isn't it? So this will become 0. I'll just get a12 here, isn't it? What else left? Derivative of h theta of x with respect to net sum. Okay, you have seen one previously z dash z, right? So this is that z dash z, derivative of h theta of x with respect to z. So if you take derivative of the sigmoid function, which means derivative of sigma of x with respect to x, you will get sigma of x times 1 minus sigma of x. You can, I'll share the slides, you can go through this and see. So derivative of a sigmoid function with respect to x, sigmoid of x with respect to x is equivalent to sigmoid of x times 1 minus sigmoid of x. So this is the complete derivation for that. So similarly, what we are trying to do here, derivative of h theta of x with respect to z1 of 3. So we are trying to do derivative of z of z13 with respect to z13. So you can just substitute this equation and get h theta of x times 1 minus h theta of x. Now substitute everything in this. You substitute h theta of x times 1 minus h theta of x times yi minus h theta of xi divided by h theta of xi minus times 1 minus h theta of x. So here h theta of x times 1 minus h theta of x in the denominator, and this term will get it in the numerator. So this and that can be cancelled, and yi minus h theta of xi times a12. That is what you will get, right? Y minus h theta of xi times a12. So if you solve all that using this actual procedure, brute force approach, what you got? Y minus h theta of xi times a12. That is what you have got, right? So if you observe this term is equivalent to delta L, which is error at the previous layer, isn't it? So let us see. If you follow the actual procedure, again you will get the same thing. Delta J equal to delta theta Lij equal to Aij minus delta I L plus 1. This is what the equation that we have defined, isn't it? If you remember. Here, you see, delta J, delta theta Ij equal to Aj L delta I L plus 1. That is what we have defined, right? If I substitute, I would get a12 times delta 13. The same thing I have got now here also, isn't it? Delta 13 is equivalent to this, and a12 is equivalent to this, isn't it? The same thing I have got, isn't it? Let us see another layer backward. Suppose I want to compute here this weight theta 111. Suppose if I want to compute with respect to this theta 111, okay, which is another layer, right? So I can write it as this, right? Derivative of j with respect to a13, derivative of a13 with respect to z13, derivative of z13 with respect to a12, derivative of a12 with respect to z12, and derivative of z12 with respect to a11. If you observe this, first let me finish this slide and I'll explain again. So this, if you compute, you would get y minus a13, which is delta L plus 1. This, if you compute, you would get delta 112, which is theta L. And this, if you compute, you will get a12 times 1 minus a12, which is g dash zl. And this, if you compute, a11. So the same thing you will get even if you do the back propagation algorithm, because it is the same formula. You can see that, right? Delta L, theta L, GMT. Okay, same thing that you are getting here. Now, it's the same thing you are getting, but you can avoid this redundant computation, isn't it? If you store this, you can avoid these two terms computation. If you store this, you can avoid this term computation. And similarly, if you store this, you can avoid this term computation also. And while doing forward propagation, you actually compute A11. If you store that, you can avoid computing this also, isn't it? So what I am trying to say is that this backpropagation algorithm is avoiding redundant computation, isn't it? If you store these terms that you have already computed at the previous layers while doing backpropagation or when you are doing forward propagation. So if you store those terms, you can actually avoid this redundant computation, which saves a lot of time. All right. So, okay, this is what the summary. So what I was trying to say is that whatever that you get when you directly compute is equivalent to whatever you get through that backpropagation algorithm. So this example we have demonstrated to justify that. Okay. Now what I want you to observe is that this term is there, right? Derivative of j with respect to a13 and derivative of a13 with respect to z13. This is equivalent to this error term here if you take the sigmoid function. But it may not be the case all the time. If you take a different activation function, this may differ. However, these terms, say for example, derivative of j with respect to a13 and derivative of a13 with respect to z13. This we actually compute when you are computing this derivative term for the weights at the previous layer. You can see that, right? Derivative of j with respect to h theta of x, which is a13, and derivative of a13 with respect to z13. These two terms you have already computed at the previous layer. I mean the last layer. It can just reuse those terms here, right? Derivative of j with respect to a13, which is h theta of x, and derivative of h theta of x with respect to z13. This you have already computed here. You can just reuse them when you are computing derivative term here, isn't it? And similarly, you might have already computed many other terms. You just have to reuse them. So what I'm trying to say is that when you are trying to implement this, you need not compute these terms again and again. You just have to store them in a cache and use them again and again. So that is how the backpropagation algorithm saves lot of time. All right. So these are the different applications of this classification of a data. Anomaly detection given. You can classify it as whether it is a cat or rat. Cat versus dog. Or anomaly detection, you given a sequence of transactions made by the customer, whether it is a anomaly or normal transaction, you can just detect that using this deep learning. Speech recognition. Hi Siri, good morning. You must have it, right? So call to Krishna. Okay, if you say call to Krishna, it will recognize your voice and then it will call to Krishna, isn't it? Isn't it? So that is based on the deep learning. Siri app, Alexa, all these are apps based on the deep learning. Audio generation, you can generate new music from the existing musics. Time series analysis. Using this, you can predict your next word, or you can also predict stock price prediction. You can do time series analysis. Spell checking. All of you might be aware of this Grammarly app, right? Spell checking and suggesting a appropriate word. All these things are done using deep learning framework only in Grammarly app.grammarly. Character recognition, handwritten characters, printed characters, handwritten digits, printed digits, different languages. All these different applications are there in character recognition. Tamil character recognition, Odisha character recognition, Hindi character recognition. All the variants are there in deep learning. Even Telugu, for Telugu also I think recently that. Vision translation, translating from one language to another, English to Japan, Japan to English, or Hindi to English to Hindi, all these things are there, and a lot of research is going on here. A lot of projects, funded projects are going on here from Hindi to local languages to Hindi, or and many other applications. This has applications in almost every domain. So with this, I conclude this session. If we have time, we can go for the hands-on. Yeah, I think I have half an hour time. I quickly go through. Usually it takes 1.5 hours to take the hands-on section. If I ask you to do step by step, but then I'll quickly demonstrate. I'll not give it to you. Okay, sir. Thank you. If you have any doubts, I'll take. Otherwise, we'll go for the implementation.
Yes, if any participants have any doubt, you can ask. Then we move on the next session.
Mr. Venkatesh, sorry, you are Mr. Venkatesh or Dr. Venkatesh?
I'm Dr. Venkatesh only.
Doctor, sorry.
No problem.
Dr. Venkatesh, my question is, how do we, the artificial neural system recognize sense of a particular temperature or smell or odor, whatever may be, a different type of sensor?
You're mistaken. See, we have not designed this artificial neural networks to do the same functionality of the neural network, right? Like detection of smell and all. Okay. So we have the current, I mean, at least the current, progress at the artificial neural network is to perform specific tasks. Like
you can take any example. You leave that
classification task or regression task. Like we have some specific object detection task.
I'm saying
tasks are there, right? For each of these things, we have an objective clearly defined. Okay. So, and we are trying to learn the parameters of this network by minimizing, in such a way that minimizes the objective function that we have at hand. Okay. But then
the sense leave that sense. It's one of the property that maybe another people might be taking. So other than that, data, how these data are interpreted or storage or programmed to learn any type of activities that mimics the human neural system.
That's what I say. For example, when we see some object, we detect that object, right? What is it?
Yeah.
Isn't it? So we have object detection. We can do object detection using it. Similarly, when we see something, we can classify it as a animal or a bird. We do all these things, right? Similarly, we can translate from one language to another language. Also,
so for that, what we have to learn properly, like a certificate course or diploma course or any Coursera course or NPTEL course, what type of deep learning and neural networking is separate course is available?
Yeah, there are many courses available. In Coursera also there are a lot of courses, but I think some of these applications will be demonstrated in this FDP also.
Okay.
Yeah, you have different frameworks, right? Like I have demonstrated feed-forward neural network, CNN, RNN, all these things are there. Along with that, you will be demonstrated with the application also, 1 or 2 applications.
So we should be started with the max also, max problem, max knowledge also we should have. Mathematics knowledge also we should have.
Yeah. Relevant. Yes.
Thank you.
Yeah, these things will be, at least a few of them will be covered in this FDP itself. And if you want more information, you can explore.
Yeah. Thank you.
Any other doubt? Otherwise, we can proceed.
Can I ask one question, please?
Please, madam.
How do you decide the number of hidden layers and nodes in those layers, and how?
This is one of the hyperparameter that you have to tune with the different
randomly.
Yeah, you have to tune different. You have to try different parameters and see which is working better.
And how does it always happen that increase in number of hidden layers or nodes will improve the performance of your model?
Yeah, mostly, but sometimes it may overfit also. There are various ways to reduce that overfitting also. All these things will be immediately discussed. After this section, I think there is a section of improving deep neural network. In that, you will be, this is what you will discuss, how to tune different hyperparameters like number of hidden layers how many number of layers should we have, how many units should we have in each layer. All these things are the hyperparameters. So how to tune them, it will be discussed in the coming section, immediate section.
Sure, thank you.
Sir, are you going to discuss BM or RBM, Boltzmann machine or restricted Boltzmann machine?
Not in this session. I'm not sure whether it is there in the total FDP or not, because I'm not the organizer. You may ask Krishna sir.
Because that is part of unsupervised deep learning.
Maybe they will cover, I don't know, I'm not sure about it, but I'm not taking unsupervised. I'll be taking another section on CNN basics, foundational concepts.
Okay, fine. Thank
Hello, good afternoon, sir.
Good afternoon, madam.
Sir, in bias, we have to calculate or we take randomly bias value.
Bias value also you have to learn. Initially, you randomly select or you initialize it to be zeros, usually zeros.
Is the मतलब sir calculate करते हैं कि we take randomly?
Yeah. You initialize it randomly or zeros, then you will learn it through the network by minimizing this error. The same, it is a parameter, right? It is one of the parameters. So you learn it is using backpropagation.
Sir, in activation function, different types of activation, ReLU is used only in inner nodes. We cannot use ReLU in our output node.
Yeah, because what ReLU says is that max of 0, z, right?
Yes.
So if you want to classify, you should have some probability at the end, right? Probability that y equal to 1 or probability of a particular class you have to get at the end, right? That is why you don't use usually.
Okay. Is basically it is used for
it is used to induce non-linearity in the network at the inner layers.
Okay, sir. Sir, why do we do back propagation? Is there any relation between outliers or something overfitting or underfitting? Why do we need to do back propagation?
Backpropagation is to learn the optimal parameters. See, when you initialize randomly initial parameters, they may not be the optimal parameters, right? That minimizes the difference between the actual and predicted outcomes. So through backpropagation, you are updating all these parameters to the optimal point.
Okay, sir.
So to learn that optimal parameters, you are using this backpropagation algorithm.
Okay. Thank you, sir. Thank you so much.
Any other doubts?
So,
yeah,
sir, for multi-class, multi-level classification, suppose I have 5 features. I have a data with
multi-class.
For classification purpose in multiple classes.
Multiple classes problem. Okay.
So if I have 5 features and I want to classify my data in multi-classes. So this backpropagation will help in that case also.
Yeah, definitely. You can have as many number of features as you need. As you want. You want to have 5 features or 5 classes?
I have 5 features, and then.
Yeah, it will help. 5 classes, 5 features means input layer size is 5 plus 1, 6, isn't it? And the output layer size is as many number of classes as you have in your data set. And you can design as many number of hidden layers as you want. By following this. You can try with multiple hyperparameters and tune that.
So which one activation function will perform in that case better in terms of performance, like this sigmoid or ReLU?
You can say that. You should have. We cannot exactly say that if I have 5 features and these many number of classes, I can use ReLU or sigmoid. Based on that, you cannot say that. But usually people prefer ReLU when they hidden layers. Usually it does well, but you cannot generalize it and say that ReLU is always better.
Okay, thank you.
Any other doubt? Is there an attendance and feedback time? I think I will share. They will share with you. I mean, Krishna sir.
Yes, yes.
Should I demonstrate this because we
Yes,
have got
yes.
only 15 minutes?
Yes,
Is
yes.
it?
You can take 20 to 15, 25 minutes. No problem.
20 to 25 minutes. I'll try to finish. Actually, this takes one full session.
Yes, yes, I know, I know.
But I'll try to finish. I'll quickly demonstrate.
Yes,
So
yes.
because I'm quickly demonstrating, guys, if you're not getting it, please don't worry about it. I'll share the code. And anyway, this is the hands-on implementation. It's a step-by-step procedure. But usually when you're using, you directly use it from the libraries. So don't be panic if you are not getting it because I'm quickly demonstrating something.
Yeah, no problem. We will share the recorded session also. And if you provide the PPTs, we will share to participants.
Yeah, sure. I can share, no problem.
Okay, okay. Thank you. Thank you.
I quickly demonstrate, but I'm not sure whether you would get it or not. It has to go very slowly, in fact. It takes 1.5 hours. Okay. So I have imported the packages. This is an implementation for a binary classification problem. So to avoid that, for simplicity, I just took binary classification problem because to start with, it is from the scratch. Everything that we have done on our own. We have not imported any existing functions like fully connected layers and all from Keras or TensorFlows, all that. Okay, so we have imported these packages. NumPy is to do all the vectorized numerical computations on the dataset. And
no, you are, excuse me, you are using some other screens.
Okay.
Okay, please share. Yeah.
I am sorry. I am really sorry.
No problem. No problem.
I just forgot. Is it visible now?
Yes, yes.
Is it visible?
Yes, yes, please.
Okay. Shall I zoom in?
Yes, yes, it is visible.
So I imported these packages. NumPy, matplotlib, sklearn.datasets, try and test split. Okay. So NumPy is for the vectorized computations. Matplotlib is to plot the graphs for better understanding. sklearn.datasets is to load toy datasets to play around the written code, and test train split is to divide the data into training and testing. Okay, for the testing purpose. Right. So we've loaded the dataset initially. I loaded the breast cancer dataset, which is a binary dataset given a set of features, and our target variable is that whether there is a cancer or not. Okay, whether it's a tumor or not. Okay, so that is the dataset we have at hand, and I've loaded this dataset into this. So load breast cancer is what I've imported already from sklearn.datasets. I'm importing load breast cancer. So if I set return xy equal to true, it returns x and y separately. Otherwise, it will return the data. We'll have to get x and y from that. So this y equal to y colon np new access, I have just we are trying to add a new dimension to the data so that it will be a column vector, just to maintain the same notions as we have discussed in the and that. So I'll just execute this. So to execute this, I can just press Shift Enter. And if you don't have Jupyter installed in your systems, you can try the same with the Google Colab also. I'll share this code with you. You can copy paste each and every cell to the Google Colab. You will get the same thing. Okay. I just want to see load the data set and see how the data looks like. I just printed the dimensions of this x and y. Loading. Oh, some error. It's not defined. Oh, okay. I did not import this. Acha, if I execute this, it may take time because next section should start at 4:15, right? So let me quickly go through it because it is taking time. I'll share this code with you. You can practice anyway. So anyway, you're not executing. I'm skipping this. So initialize parameters in a deep neural network. So for this, it takes layer dimensions as the input. How many dimensions? I mean, how many units are at layer 1? How many units are at layer 2, and so on till the last layer. So if we have some 10 layers, we pass 10 element list as an input to this. Okay, with each entry specifies that how many units are there at a particular layer. So entry 2 specifies that how many units are there at layer 2, and so forth. Okay, so after getting that layer dimensions, I can initialize the parameters, correct? So if I have some three units at layer 2 and 3 units at layer 1, I can have a 3 by 3 parameter or a weight vector at that particular layer, isn't it? So like that I will install. I mean I will initialize. So I'm initializing for L equal to 1 to L, that is starting from the layer 1 to last layer. I'm initializing the parameters. Okay, between the layers there are parameters. So I have got two different parameters, W and B. So WLBL, I am terming it as WLBL. So W at layer L is WL, B at layer L is BL. So I just initializing random values with the dimensions of layer L times layer dimensions L minus 1, isn't it? So I'm just initializing some random values with the dimension of L by L minus 1. Layer dimensions I know. So according to that, I'm just initializing the matrix multiplied by 0.01. This is some random initialization. B is initialized to zeros with the layer dimensions of 1. So usually how many bias units I have? If I have 10 units at layer 2, I'll have 10 biases, right? Because at each and every node, I add a bias term. So if I have 10 units at a particular layer, I'll have 10 bias. So layer dimension of L by 1 is the size of this bias. Okay, and I am just returning these parameters, isn't it? So I just initialized it to some random values and returning it. So this is initializing parameters in the deep network. This is a forward propagation module in which we first compute the net sum and then we pass it to the sigmoid function. For that I have first of all individually implementing the individual functions, then I integrate all that. So linear forward function, it means that linear net sum I have to compute, I require these three things, right? Activation unit, W and B. So and the net sum is equivalent to np dot W comma A, which is dot product over W and A, WA plus B, which is theta transpose X in fact. Okay, theta is W, X is A, and B is your bias, X theta naught, isn't it? So you observe here, I'm just storing these values A, W, and B because while doing back propagation, I need not compute them again if I store them. So to avoid that recomputation, I'm storing them in a cache. So I just return Z and cache. Alright, and then sigmoid function. Sigmoid is, what is sigmoid? 1 by 1 plus e power minus z, isn't it? So I receive z as the input. I compute 1 by 1 plus e power minus z, which can be computed using np.exp. np is the numpy. From numpy library, you can get this exp method minus z. And I store this also, you see, z also I am storing here to avoid redundant computations. So I just pass a and cache here. Now comes, you can integrate all these two things here and compute linear activation forward with a particular activation function. If it is a sigmoid activation function, I just took sigmoid because we have only covered sigmoid. So activation equal to sigmoid, I just compute linear forward, then I get net sum in Z, linear cache in cache, and passing this net sum to the sigmoid function, I can get activation unit A, isn't it? And this is the activation cache I am getting. So I store this linear cache and activation cache in a cache. And I'm returning A and cache. So this cache is to avoid redundant computation. Just remember that. Now I have all the functions are, all the functions are ready for me to do this forward propagation for L layers, isn't it? So I have net sum function, I have activation function, all these functions are there, isn't it? So I can just compute L model forward, which takes X and parameters as the input. X is the input and parameters anyway, the initialized parameters, isn't it? And caches I am initializing to 1 because you have to store caches at each and every layer. So I initialize A equal to X, which is the, for the first layer activation, I initialize to A, L equal to length of the parameters. And then for L in range of 1 to L, that means that we are doing forward propagation, right? So this we have to compute activation units at each and every layer, layer by layer, correct? Starting from the first layer. So I store A previous equal to A, and then linear activation forward, isn't it? That computes this activation unit for a particular layer, isn't it? By passing the parameters at that layer and activation unit that you want, either sigmoid, ReLU. Yeah, see, for ReLU I did not implement. And this you repeat till L minus 1. And finally for the last layer also you can compute the same for capital A, isn't it? So this I have separated because for the hidden layers you can have a different activation function if you want to do so. Okay. So, and then we are appending cache at each and every layer. Means that we have a list of caches, isn't it? And then I can return this AL, which is the activation at the output layer. Also, it is a prediction, H theta of X and caches. Okay. Now, once I do this forward propagation, I can compute the cost. So for the cost function, it requires the prediction and the actual value, AL and Y, isn't it? So you can compute this equation, right? 1 by m. This is the cost function that we are using, right? So that is computed here using np dot multiply, np log a, all this. So this is computed here in log probes, and then you are taking the sum over 1 by m here. This is the cost. Okay, and returning cost. This is cost to reduce the dimensions to want to have a scalar value here in the cost. That is why it is squeezed. Now comes, so you have given inputs, forward propagation module, to which you have computed all these activation units till the last layer. At the last layer you compute the cost, and then you have to back propagate, correct? So linear backward and sigmoid backward, activation backward. These two things here, right? So if you have finally what you have to compute, you have to compute derivative of j with respect to a particular parameter w, isn't it? So if you have dz, that is derivative of j with respect to z, you can compute dw and dv using this equation. This is the same thing that whatever that we are doing there, dz and al, we have seen that, right? If you want, I mean, it may take time, but yeah, let me quickly show you. Sorry. So dz is this whole term, and this is that. Al is this last term, this term. Okay. And that is how we compute dw and dv, and dA is derivative of L with respect to A. Okay. Yes. Alright. So linear backward, you just have to compute these three TW. Once you have dz and cache have all that values, right? A, all these are already computed when you are doing forward propagation and stored in a cache, isn't it? So you can access them and compute this dw, db, and da previous. All these three, dw, db, daw. The same things I have used here also. You can go through it. So dw, db, and da previous are calculated. And now sigmoid backward, we just have to add extra, multiply with extra term here. That is what you are doing here also. If you see this extra term. Okay, so it changes based on the activation function. So that is why it is separately given. Okay, so this is multiplied, right? So dA cache dz equal to dA times s times 1 minus s, where s is 1 by 1 plus n to the power x squared minus n, isn't it? So you have sigmoid backward, you have linear backward. Now you can have linear activation backward. Dz you can get by doing sigmoid backward. Once you get dz, you pass it to the linear backward and can get dw, dv, dA previous. Okay. Once you get dB, dw and all, you can do L model backward, isn't it? You can also update the parameters, isn't it? So L model backward, you're computing DAL at the last layer and then using this DAL to pass it to the linear activation function. You see, DAL starting from L minus. Okay, DAL. Okay, so and then you're calling this linear activation backward till layer 2, isn't it? And then now once you get that dA, dW, dV, you can calculate. This is stored in the gradients. So you have computed the gradients. You just have to update the parameters now. So derivative of j with respect to a particular parameter is computed and stored in these gradients. How do you update? WL equal to WL minus alpha times derivative of WL with respect to WL. And similarly, BL equal to BL minus alpha times derivative with respect to BL. That is how you do it, right? So you know this dW and all that is stored in gradients. You also know the parameters, that is W, V. You also know the learning rate. Once you pass these parameters, for each layer, you can update these parameters at that layer. WL, BL is equivalent to parameters of WL minus learning rate times the corresponding gradient. Similarly, for BL also, parameters of BL is equal to parameters of BL minus learning rate times gradients of that particular layer. Okay, I am just quickly going through it because we don't have time, but if you don't get it, please don't worry. You can go through it. If you have any doubts, you can approach me also. So this is L layer model. You can do this repeated for all the layers. So L model backward, you can, you have L layer forward, L layer backward also, right? So you can develop L layer model, okay, which takes input as X, the output also, layer dimensions, learning rate, number of iterations, which is the convergence condition. How many number of iterations you have to repeat. So for all the iterations, 0 to number of iterations, you first do forward propagation, then compute cost, backward propagation, then update the parameters. So this you repeat for 1500 number of times, which is the convergence criteria. So you are doing forward propagation, for computing cost, then backward propagation, then updating parameters. Give me 1 second. Sir, I am taking class. May I call you later? And backward propagation, then once you do the backward propagation, you get the gradients. Using that gradients, you can update the parameters, and you're just trying to append this cost to print how is it. Whether it is decreasing, cost is decreasing at every iteration or not. If you repeat for every iteration, it is time taking. That is why you repeat for every 100th iteration. And you are just plotting that. You can see the cost is decreasing. Isn't it? So this is how you load the data set. You divide it into training and testing, and then you pass this training data to L layer model that we have developed, X train, Y train, layer dimensions, number of iterations, and using these parameters that you obtained from the network, you can test it. So these parameters and X test, you pass it to L model forward, which will give you the Y prediction. Once you get the Y prediction, you can compute the accuracy of the model by passing it to accuracy score. So you can, this 63% accurate, which is not good. You can try with different hyperparameters and tune up. And we have not used regularization also in this. You can try regularization also. So I think I have finished on time, but I don't know whether you understood it or not. If you have any doubts, you can approach me. This code anyway I will share. Slowly go through it. You definitely will understand. If you stuck somewhere, please you can call me or approach me during the channel. Thank you very much. I'm done, Krishna sir.
Yes, thank you very much, sir, for your nice presentation and through the examples. If anyone
Sir,
want to
can
ask
I
any
ask
question,
one question, sir?
yes, yes, sure, sure, sure. You can ask.
Yeah. Sir, artificial intelligence, can we connect with this neural networking and deep learning process? Artificial intelligence, can we connect, how can we connect this artificial intelligence with the neural networking and deep learning process?
See, neural network or deep learning. Deep learning actually uses artificial neural networks. Okay, so you can
No, no,
consider
I'm
that
asking
both of them.
intelligence.
Yeah.
Artificial intelligence, AI,
Yes,
I'm
yes,
asking.
this deep learning is you can imagine it as a subset of artificial intelligence.
Oh, okay, okay, okay. Okay, sir. Thank you.
Any other doubt?
Sir, you have used sklearn data, that is inbuilt data from library itself. So can we, any other approach, we can use our own CSV file, data file?
Yeah, you can load your own data. Load CSV file. Load CSV is the method to load.
Okay. Okay, thank you.
Any other?
Okay, I think there is no question from the participants. So I'm very much thankful to you, sir, for accepting our invitation and delivering 2 different lectures. Again, thankful to you. Thank you very much. Okay, so the next session will be start on 4:15. So 10-minute break here.